Hey, so we're doing chapter 4, and we're talking about applications of derivatives, right? And so what do you hear when you hear the word applications? Yes, you're going to use derivatives, but what evil word do you hear when I say applications? One word. What kind of problems? One word. What kind of problems? Blank problems. One word. Word problems, right? Word problems. So there's a lot of reading and writing in this section, okay? But when things get complicated, and they do very quickly, I am going to simplify. So for example, we talk about related rates, right? The very first related rate I talked about is calculus, dropping a stone in a pond, right? And what happens over time, the area is changing, the radius is changing, the circumference is changing. These are related rates, all with respect to time. Think of a cup of coffee. Think of a cup of coffee, you just poured it, right? What happens to it as it sits in the classroom? It cools off, it goes to room temperature, right? So related rates, right? Can you picture an hourglass with the sand? You know what I'm talking about? Where they used to turn it over, or your game, you would play a game and you turn a little hourglass over and your turn is over. That sand piling up, right? What's happening to that pile of sand? Well, there's a volume, right? There's a height, there's a base, right? So all of those things are changing. So it can go on forever, and the book does go on forever with it. What I try to do is simplify it and say you'll only have this type of problem or this type of problem, right? So when I say we have a quiz on related rates, you make sure you do every problem like those two types of problems, right? Same thing with optimization. Optimization gets very, very complicated. If you could think about, I'm making boxes for Amazon. My company's making boxes for Amazon. Okay, you right? You ever order something from Amazon? All kinds of different boxes. But what am I trying to do? If I'm making the boxes, I want to minimize the amount of material I use, but maximize what? The space, the volume. And so that's optimization, right? And so again, there's lots of ways to think about that, right? Again, what I will give you will be one or two types of problems. So you'll be able to look at my chapter 4 tests and my final exams, and you'll see there's always that type of problem on the test. So guess what? It's going to be the same for you because I'm so lazy. I don't want to change it, right? And you are the sole survivors. So I'm trying to really give you a chance, right, to do well. I'm trying to give you a chance to do well. Daniel, here is your test and the project that we're starting. And if your final exam grade is higher than your midterm grade, I will replace. It doesn't work the other way, of course, right? If your midterm exam is greater than your final exam grade, I don't replace. Because the final exam will have everything on it. The midterm does not have everything on it. Maranata, you hear that? Final exam grade higher than your midterm, I will replace the midterm exam grade. Still a chance for clean grade. Oh, and I guess that's on tape now, so you got me. Right. It's recorded. So related rates, absolute min and max, first and second derivative test. Notice I cut out section 4.4, that's graphing. So you'll see when we learn these different tests, it'll tell us if the graph is increasing or decreasing or concave up or concave down. And so you really should be able to graph any function without a calculator after this section, okay? But I don't bother doing it because we're going to still have our calculators. L'Hopital's rule we already did, so they're crossed out. And Newton's method is going to be project only. So there's only 4 sections to cover here, but I still want to talk about Newton's method today, okay? So you all have the project. Again, it can be worked on in a group of up to 3 people. You can work on it alone, you can work on it in a group of 2, you can work on it in a group of 3. It was not written by me. I forget which university the professor's from. You can find the solutions. If you're good at searching the web, you can find the solutions, okay? But on the last page there, or in my rubric, right, it tells you what the things I want you to include. So if you just give me the solutions from the web, it won't give me everything I want, okay? I want graphs and I want tables. So you're going to do a little programming in Excel for this, okay? So, but let's talk about it first. Now, if you look at the first page, it's all blah, 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 blah. And it's written at a high level of sophistication. And if you're noticing me, I'm saying things pretty simple. If you have fractions within fractions, get me a single fraction, right? So I'm always trying to say things as simple as I can. So basically, this first part of what I'm going to talk about is part A and B. And that's what they talk about in on that first page, okay? Part C, I'm going to do today. Part D is going to be the one that you're working on. Part E is the tricky one, and I want you to write this right on the paper right now. Algebraic. The answer is algebraic. I don't want numbers. I want everything kept abstract. So at the end, you're supposed to show that the relative error, right? The new relative error. Do you see that in almost the middle of part E? It says rel x sub n plus 1. The new relative error is the old relative error squared. The new relative error is the previous relative area squared. What kind of error would we like in any problem? What kind of error would we prefer? How much error? 0. Right? So 0 would be great, but it could be 1% error. That's still pretty damn good, right? If it was a 1% chance the plane would crash, would you still fly to Hawaii? Yeah. I would. Sure. So, you know, but if you think about it, if your relative error is small, what happens when you square it? If your relative error is 1/2, 1.5, right? What do you get when you square it? 0.25. So if you're squaring very small error, it's going to 0, right? So this is a key point here of what we're doing. Remember, and what is Newton's method doing? It's calculating square root of 2 for me, right? So on my calculator, when I press square root of 2, it does this program. In part F, so part E is the tricky part, okay? Now you can ask me anytime. You can ask Dr. Early, he's worked on this project before, he knows it, okay? You can ask me, you can ask someone, and I don't care what you do. You could find the solutions and then just rethink it, right? But keep it algebraic, okay? And so as we get further in the semester, as if you have questions, it's fine to ask about the project at the beginning of class, via email, in office hours. For part F, notice there's 3 parts, 1, 2, and 3, right? Roman numerals 1, 2, 3, you see that? So if you're working alone, you just pick one of them, and you do it yourself, right? If you're working in a group 2, you pick 2 of them, each of you doing one of them, right? Does that make sense? And if you're working in a group of 3, all 3 of you do one of them, so that they're all 3 covered. And what's happening is in Newton's method in this section, section F, the method fails. And it's 3 different ways the method can fail, and these will demonstrate those 3 ways. But you only have to do one of them, one of the 3. So you might want to start all 3 of them and decide which one you like, right? You know what I mean? If you're working alone. For that one, I definitely want a graph and a table. For part C, we want a table. You'll see me do a table, maybe a graph. Anytime you have a solution, a graph might be interesting. And I don't care how you write it. So meaning you could handwrite it, right? You could, you're going to use Excel or anything you want. So I guess you could use, what is it, Sheets for Google Sheets. You could use that. You know, you could use any program you know. If you're a programmer, you could certainly do it in Python or whatever you're programming in. For me, it was always PHP, but that was the programming language that I was using the most. And then I'll show you where you get some nice graphs from, okay? All right, so let's talk about Newton's method here. The method is to find solutions or roots, okay? So for example, if I have some function, right, f of x, and I want to find the root, I want to find this 0, right? What I do is I make a guess, okay? I make a guess. So I'll make a guess here. So this is, I'll call it x sub naught, or x sub 0, or x null, the initial guess, right? And what I do is I go up to the curve, right, to the point x sub 0, f of x sub 0, right? And I draw the tangent line. And look at where it hits. Look at where it hits. It hits close to the 0, doesn't it? Now, depending on the severity of the curve, right? And this is where some of those in part F where it fails, it could go further away from the root instead of closer to the root. So this guy gives me x sub 1. And that's what I like to call x next. X sub 1 is the next guess. Because what I'm going to do is repeat the process, rinse and repeat, right? So what do? I go up to the curve to x sub 1, f of x sub 1, right? Draw the tangent line, yes? And look at it, it's even closer now. So eventually this thing is going to run into the answer. So when I say square root of 2, on my calculator, I say square root of 2 with 5 decimal places. Newton's method goes through the process until those 5 decimal places keep repeating, and then we know we got to 5 decimal places. Right? Does that make sense? And you'll see that happen today. So I keep doing Newton's method, and I keep getting closer and closer, but my first 5 decimal places never change. I got it. I got the answer. Right? Is that making sense at all? So you can see on this particular picture, I started with an initial guess, and then I got a next x sub 1, and then I got what? X sub 2, right? I got x sub 2. So I'm going to keep, it's called an iteration, right? It's called an, what? What? Yeah, the tangent. So where the tangent hits the x-axis, that's my next guess. Yes, you with me? Okay, nice. So let's figure out here what we got, because we know the tangent line. What's the tangent line equation? Okay, y minus y1. That's going to be f of x sub 0. Remember, my first guess was x sub 0. Equals m, but what's m? Derivative f prime of x sub 0 times x minus x0. Remember, I'm always starting from that initial guess. And how am I going to make the initial guess? Well, you could just guess randomly, right? Like in one problem, we're doing the reciprocal of pi, right? How big is pi about? 3.14, right? Proximate. So imagine I'm going to find the reciprocal of it, 1 over pi. What's a good guess? Well, 1 over 3 is pretty good, right? 1/3, so 0.3 is a pretty good guess for the reciprocal of pi. So it'll be obvious what you do, or sometimes you'll have to you could use Desmos to get the real answer. You could use your calculator to get the real answer, right? What do I know about x and y on this? Look at this green. Remember, the green is my tangent line, right? Yes? The green is my initial tangent line. What do I know about x and y at this point? Well, what letter is x on my page here? What letter is x? Not x0. x0 is here, right? And x0 is x0. So, but what is x? Not what? X sub 1. X sub 1. And what do I know about y sub 1? What height is it? 0. Okay, so look at what happens to my tangent line. This is Newton's method, right? I've got 0 minus f of x equals f prime of x all times x next minus x. So first of all, notice that I've changed all my x sub 0s to x. I don't like using a subscript, so if I can not use it, I'm going to not use it. Right? And look at the picture again, right? So,
does this still mean x of 1 minus x?
Yep. So this is now x comma f of x, right? This is my tangent line. This is m equals f prime of x, right? And what is this point? X next, comma 0.
Is it possible for you to write like an abstract version of the problem that would make it easier?
Yes, I'm going to actually do part C. Yeah, yep. We're just talking theory right now, right? So, what don't I know? Well, I made the guess for x, right? And I put it into the function for f of x, and I put it into the derivative for f prime of x. Yes, so I know all of that. So what don't I know here? X next. So that's what I'm going to solve for. I'm going to solve for x next, right? So what do you want to do? I've got minus f of x equals f prime of x times x next minus x. What do you want to do? I'm going to solve for x next. What do you want to do? Nice, divide by f prime, right? So I got x next minus x equals negative f of x over f prime of x. You can already see one of the issues when Newton's method won't work. What's the issue when Newton's method won't work that you see right now on the right-hand side? The negative is not a problem.
Zero.
If I get a derivative that's zero, I cannot do Newton's method. Okay? Because I can't divide by zero, right? Everyone okay with this step? I switched sides, by the way, right? I switched sides and I divided by f prime, right? Everybody okay with that? Good, all I have to do now is move the x over and I got it. So this is my Newton's method. The next guess I'm going to make is going to come from the first guess minus the function at the first guess divided by the derivative of the first guess. And this is what I'm going to iterate. Iterate meaning, right? Take the result and put it back in. Take the result and put it back in. Take the result and put it back in.
Wait, okay, at the very beginning, why is there a negative f of x?
So remember, it's y minus y1,
Okay.
right? From the slope formula or the equation of the line formula. Yep. So this is it. So this is part A and B. I just did part A and B for you. But reread it and write it up yourself, okay? So this is what the whole first thing is saying. And then part A says, well, how do I get the next guess? And then can I write it nicely as part B? How do I get the next guess? And can I write it simpler? Right? Yes. Now, if you read this section of the book, you'll see this exact formula, okay? But it's going to write it like this. X sub n plus 1 equals x sub n minus f of x sub n divided by f of prime of x sub n. And so, right, so all of the x sub n's, I'm saying, well, just call it x, right? I just replace all of them with the same simple thing. And then, can you see how this is x next? N plus 1. So if the n was originally 5, right, if it was my fifth iteration, right, then one more would be 6, right? So that's the n plus 1. It's telling me that's the next one, right? Does that make sense? It's just a counter, right? That subscript is a counter. X sub 2 minus x sub 1. First x, second x, right? Cool. All right, looking at part C, we're ready to move. Yes? Everybody okay here?
Wait, can you go just back up? Really quick?
Yep.
Okay, cool.
Yeah, no problem. I'm not in a rush. Good. Nice. So we're gonna come back to this piece, right? This is what we're going to be using the whole project, okay? But we're gonna do it, right? So we're gonna start this first one for you. You make sure you do it over. So in part C it says I have an equation of 1 over x equals what? 1 plus x cubed. And of course I know how to graph those, right? 1 over x is easy. And x cubed is easy, so if it's 1 plus x cubed, I just shift it up, right? All that pre-cal work we did, right? Shifting up the x cubed function. And it's saying there's one positive solution, and there it is. If I do this on Desmos, I get a really quick answer, so that's what I'm going to do, okay? I think the priority registration is in 2 weeks. But double check me on that for summer. You can register for summer 1 and summer 2 at the same time. So I think it might be April 1st. I don't quite remember. What is the date today? It's 22nd. I think it's 1 more week. So anyway, I had y equals 1 over x, right? And then I also had y equals 1 plus x cubed. And you can see my positive answer right there, 0.724. Remember, I'm trying to find the x, right? Newton's method is finding me the x. So I got a good place to start. What's my good guess to start? What do you think? 1 works? What else? 0.5, sure. 0.7, right? I can easily pick any of those to start. You'll discover in the project that sometimes if you start at the wrong guess, you don't get the answer. So, but on this particular one, all 3 of those starting points will work. So we've got to manipulate this a little bit to get me what Newton's method gets me, a 0, right? Newton's method gets me an x-intercept, right? So I've got to create a function here. I'll create the function f of x equals 1 plus x cubed minus 1 over x. So there's my function. So if I have 2 things equal to each other, like x equals square root of 2, I'm going to create the function f of x equals x minus square root of 2. Yes, you with me? So I'm finding a root. I need to be able to find an intercept. That's what Newton's method gets me. What else do I need for this x next? Look at our formula. X sub next equals x minus f of x over f prime of x. What else do I need? The derivative. Who's got it? Nice. Nope. Huh?
1 over x squared.
Thank you. I was going to ask who the hell taught you Calc 1? I did. So there it is. There's my derivative. Everyone agree? Hello? Does everyone agree? Yes? Nice. I want to create my x next here, right? Using this formula. And I want to make it pretty, okay? And that's in quotes, right? Because we all know some of us don't think this math is very pretty at all. But we want to get a nice function to deal with, okay? So let's see. X next is going to be x minus, my function was what? 1 plus x cubed minus 1 over x divided by 3x squared plus 1 over x squared. Yes, you with me? Not very pretty. Why? That's right. It's not. I want one completely factored term, and it's probably going to be a fraction. So I don't like the fractions within fractions, so what am I going to do to this? Multiply by x squared over x squared. I am going to do that, but I like to clear fractions first. So it looks like I get, what, x squared plus x to the 5th minus x. Uh-oh. Over what, 3x to the 4th plus 1. We agree? Now in LCD, so x times 3x to the fourth plus 1 minus x squared plus x to the fifth minus x all over 3x to the fourth plus 1. Everybody with me? So now I'm going to distribute and combine like terms. And I get my x next. It looks like what? 2x to the fifth minus x squared plus 2x all over 3x to the fourth plus 1. Anyone else get the same answer? I really want to double check this because I'm worried about doing what I'm going to do in Excel with the wrong formula. Anyone else get the same answer? Yes, thank you. This is my Newton's method iteration to figure out what is my next guess, right? We already said that we could start at 1, we could start at 0.5, we could start at 0.7, right? You'll see all of them will work in this case. How do I know it works? I eventually get the same result over and over again, right? Okay, so here we go in Excel. Yes, sure, yeah, where are you?
Yeah, right there.
Okay. Oh, picture, sure.
I was an idea.
Yeah, no problem. Okay, next. Yeah,
Thank you.
you got it. And this is part C, remember, right? In the project, yes? So we're going to Excel here. I used to be an anti-Microsoft person when I lived in California. I was a tree hugger. I was a vegetarian. So I'm going to call my first column X and my second column X next. And we already said we could start at 0.5, right? So there's my first guess. In my next column, I'm going to be putting in that formula, but I'm going to be referencing X as A2. Do you see my cell A2? A for the column, 2 for the row. A2 is now my X value. So when I write this for Excel, I'm going to say X next equals 2 times A2 to the fifth minus A2 squared plus 2 times A2 all divided by parenthesis 3 times A2 to the fourth plus 1 close parenthesis. When I go into Excel, I'm referencing my guess cell from A2. Okay, ready? So open parenthesis, so I need equal, that's important that I put the equal, equals, parenthesis, right? My whole numerator, right? You with me? 2 times, yes? A2, usually we use capital, caret to the fifth, correct? Minus x squared, is that right? Minus A2 squared? So minus A2 caret squared, help me, plus 2x, yes? Yeah, 2 times A2. Good, close parenthesis, that's my whole numerator, yes? You with me? Divided by, open parenthesis for my whole denominator, 3x to the fourth plus 1, is that right? So 3 times A2 caret to the fourth plus 1, close parenthesis. Everybody okay? Anybody need a picture of that before I leave this cell? Nice. Enter. 0.68. I know the answer was closer to 0.7, right? But what I'm going to do is I'm going to take this entry in B2 and put it in A3. So I write equals B2. And it's going to copy that answer now to my X column, because what am I going to do? Repeat the process with that new X. So what I do is I'm just going to fill down here. So I highlight, I'm holding the shift button down, and I'm going to do Control D, will fill down, right? And then I'm going to do the same over here, because I don't want to have to copy my answer all over again. Control D will fill down. And look how fast it got to the answer. How many iterations? Well, I took a guess, iterated. After the second iteration, everything's the same. Pretty quick. What's nice about this is I could change my guess right away. So if I start at 1, it only takes me 1 iteration, right? I guess, I get an answer, I iterate it, go back into the machine with it, got it. 0.7. Really quick, right? What do you think? Now, I'm going to show you a graph, and then we'll take a little break. What time? Perfect. So let me show you a graph, and we'll take a quick break. I like the graphs on... Now, when you do the project, right, you certainly can copy your table by hand. You could email me the Excel file. You could, it's nice when you, and you wouldn't need all of this, right? But if you do put, if you copy this into Word, it's pretty. So whatever you do is fine. I don't want you spending a lot of time on the little details, right? There's an 80-20 rule. Do you know the 80-20 rule? 80% of what we do in life is a bunch of wasted time bullshit, and 20% of what we do actually is meaningful. When you're sitting there changing the fonts and the margins and waste of time, right? Just do the 20% is what you need. Right? I like to say, dare to be mediocre. Dare just to get something done and see what it is, instead of having this obsession with having to be right and perfect, and you'll get paralyzed by it, right? Just go for it. Same thing on your test. It's not going to kill you to fail the test, right? It's not like some stupid movie where if you don't solve the math puzzle, the building blows up. It's not going to happen, right? So you just go for it, right? Go for it. All right, graph. I like GeoGebra, but like Desmos, it will run constantly. So it's geogebra.com, geo as in geometry, and then Gebra like algebra. So geometry and algebra kind of mixed together, geogebra.com. There's a little search button. This will come in a lot of help in Calc 2 when you do something called revolutions of solids. So it's hard to do this part in Calc 2. It's nice to have a visual. GeoGebra will give you a great visual. When you go to Calc 3, you'll need to do something else. Wolfram Alpha or MATLAB. because you're going into 3 space. So you need an X, a Y, and a Z coming out of the board, right? So Newton's method. If you remember that first graph I did, I had a tangent line hitting, another tangent line hitting, another tangent line hitting, getting closer and closer, and that's kind of what I want here, right? So I think the one that's decent is this Eric Jacobson. It looks like the Daryl Funk. I like his name better, so Daryl Funk. So you can see where I'm getting all of my solutions at. This will be really nice in the ones in part F, because one of them is going to run away from the solution. The tangents will just shoot it way far away, and then the next one will shoot it even further away. One is going to oscillate, and one is going to be divide by 0. So those are the part F is, one is a runaway, one is an oscillator just back and forth, and one is a divide by 0. So, you can get a nice picture, and again, you can just copy the screen, control, print screen, and then paste it in something, or hand draw it. I don't care, right? But I'd rather not do the work. I'd rather just get GeoGebra to do the work for me, because I'm lazy, and I have better things to do, right? I think that's probably true for all of us. Maybe you're not lazy as me, but I'm pretty lazy. I don't feel like doing anything. Let's take a 10-minute break. So come back at 10:10. 9-minute break.